Scientists just did something that was once considered almost impossible. They captured a direct image of a planet outside our solar system. Not an artist's impression. Not a computer simulation. Not an illustration based on scientific data. An actual image produced from light coming from another world. The planet is more than 100 light-years away, orbiting a young star surrounded by a vast disk of dust and debris. And what makes this discovery so important is not simply that astronomers found another planet. It is that they were able to see the planet itself. For decades, humanity discovered most exoplanets indirectly. Astronomers watched stars and searched for tiny changes in their light. If a planet passed between its star and Earth, the star became slightly dimmer. That tiny dip could reveal that a planet was there. It was an incredibly powerful technique, but there was one major limitation. We usually couldn't actually see the planet. We could detect its effect on its star, calculate its size, estimate its orbit, and sometimes study its atmosphere. But the planet itself remained hidden in the glare of its parent star. That is why direct imaging is such an extraordinary challenge. Imagine trying to photograph a tiny candle sitting directly beside an enormous searchlight. The searchlight is so bright that the candle disappears completely. That is essentially what astronomers are dealing with when they try to photograph an exoplanet. A star can be billions of times brighter than the planet orbiting it. The planet's faint glow gets buried beneath the star's overwhelming light. This is where the James Webb Space Telescope becomes incredibly powerful. Webb's MIRI instrument includes a sophisticated coronagraph designed to block and suppress the light coming from a star. Instead of allowing the star's overwhelming brightness to dominate the detector, the coronagraph creates an artificial mask that hides much of the starlight. One of its techniques uses a 4-quadrant phase mask, which manipulates the incoming light through interference. The goal is simple. Block the star. Reveal what is hiding beside it. Even after the coronagraph does its work, some unwanted starlight remains. So scientists use extremely sophisticated image processing techniques to remove additional stellar glare and other sources of noise. Layer by layer, the overwhelming brightness is reduced. And eventually, something extremely faint can emerge. That is what happened when astronomers observed the young star system known as TWA7. The system is located roughly 111 light-years from Earth. The star itself is extraordinarily young compared with our Sun. Our Sun is about 4.6 billion years old. TWA7 is only a few million years old. In cosmic terms, it is essentially a newborn star. Around it is a large disk of dust and debris left over from the formation of the planetary system. Astronomers had already observed structures within this disk. There were distinct rings and gaps. And those gaps were interesting because planetary systems often develop these structures when planets interact gravitationally with surrounding dust and debris. A sufficiently massive planet can sweep material out of its orbital region, creating a gap. For years, astronomers suspected that an unseen planet might be responsible. But suspicion is not confirmation. They needed to find the planet. Then Webb looked. The telescope detected a faint infrared source near one of the gaps in the debris disk. At first, scientists had to be extremely careful. A faint object in the background could potentially be an unrelated galaxy or another distant source that simply happened to appear in the same region of the sky. So the team examined the data and calculated the probability that the source was merely a background object. The evidence strongly favored the interpretation that the source belonged to the TWA7 system. In other words, they had found something that looked like a planet. And that planet became known as TWA7b. The discovery was especially important because of its relatively low mass compared with earlier directly imaged exoplanets. It is estimated to be roughly Saturn-like in mass. That is a major step forward for direct imaging. Earlier directly imaged planets tended to be much more massive. The reason is simple. The more massive and younger a planet is, the more heat it can retain from its formation. That makes it brighter in infrared wavelengths. A smaller planet is much harder to detect. JWST is therefore an important demonstration of how far direct imaging technology has advanced. The planet is also extremely far from its star compared with Earth's distance from the Sun. Its orbit places it far out in the system, in a region where the surrounding debris disk becomes particularly important. And that creates another scientific opportunity. Astronomers can compare the planet's position with the structure of the debris disk. If the planet is actually responsible for creating the observed gap, then the system provides a real-world laboratory for studying how planets shape the material around young stars. For decades, scientists have used computer models to predict how planets interact with debris disks. Now they can compare those models with an actual planetary system where the planet and disk structure can be observed together. That is a major scientific advantage. But there may be another fascinating feature. Researchers have considered whether material associated with the planet's orbit could be similar to Trojan populations. In our own solar system, Jupiter has enormous populations of asteroids sharing its orbit. These objects occupy gravitationally stable regions ahead of and behind Jupiter. If similar structures exist around JWST, studying them could provide another clue about how planetary systems develop. And that is where this discovery becomes much bigger than one photograph. It gives scientists another way to study planetary formation. For most of human history, we didn't even know whether planets existed around other stars. Then, in the 1990s, astronomers began confirming the first exoplanets. Suddenly, the universe changed. We learned that planets were not unusual. They were everywhere. Thousands of exoplanets have now been confirmed. Some are enormous gas giants. Some are smaller rocky worlds. Some orbit their stars in just a few days. Others travel around their stars over many years. Some exist in systems nothing like our own. But finding them and seeing them are two very different things. For years, astronomers could tell us that a planet existed without ever showing us the planet itself. Now that is beginning to change. Webb has demonstrated that direct imaging can reach smaller and fainter worlds than earlier generations of telescopes could manage. And that creates an obvious question. If we can directly image a planet comparable to Saturn, how much smaller can we go? Could we eventually photograph something closer to Neptune? Could we someday directly image a rocky planet? And ultimately, could we photograph an Earth-like world? That is the dream. But Earth-like planets are dramatically more difficult to see. A rocky planet is much smaller and fainter than a gas giant. If it sits close to its star, the contrast becomes even more extreme. The star's light can completely overwhelm the planet. That means future telescopes will need even better coronagraphs, more sensitive detectors, better optics, and far more advanced image processing techniques. One of the major observatories being developed to push astronomy further is the extremely large telescope in Chile. With a primary mirror roughly 39 meters across, it is designed to provide an enormous increase in light-gathering power and resolution. Observatories like this could eventually push direct imaging toward smaller planets. And space telescopes will continue to play a critical role as well. The future is not about one telescope replacing another. It is about different observatories working together. One telescope might discover a planet. Another might measure its atmosphere. Another might study its orbit. And another might eventually produce a direct image. That is how astronomy advances. One observation builds on another. One instrument opens the door for the next. And Webb has already transformed our view of exoplanets. It can study atmospheres and detect molecules such as water vapor, carbon dioxide, methane, and other compounds. These measurements can tell scientists about the chemistry and physical conditions of distant worlds. But direct imaging adds something fundamentally different.